In this video, we are going to find all functions that send positive integers to positive integers and satisfy the equation that for all positive integer n, f of n plus 2 times f of n equals 3n plus 5. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. When most functional equations require a lot of creativity and skills in problem solving, such as finding whether functions are, for example, injective, surjective, bijective, and to put some very complicated substitutions, this functional equation only requires the most elementary knowledge. In fact, we can find out what functions can satisfy this function equation only by plugging the smallest positive integers. For example, when n equals 1, we'll have f of 1 plus 2 times f of 1 equals 8. Now from this we can know that this number, since 1 is the output when 1 is put inside the function, and by definition is also a positive integer. And same for this term. So that means this f of 1 must be a positive integer that is less than 8. If not, when this number is added by 2 times f of 1, it will be larger than 8. At the same time, we know that 2 times f of 1 is not just a positive integer, but it's also even positive integer. And that means we can start considering values, say 2, 4, and 6, and we can skip some of the even smaller values. So from this we can say that f of 1 is even and f of 1 is less than 8. And that means we only have 3 cases to consider, which is f of 1 equals to 2, 4, or 6. So let's see what happens when f of 1 equals 6. We'll start trying from the largest value. Indeed, if f of 1 equals 6, then putting back to the equation above, then we know that 2 times f of 1 is equal to 2. That means f of 6 is equal to 1. Then all the things we know about this equation is that f of 1 equals 6 and f of 6 equals 1. So what we can do is just to put n equals 6 into the given equation. So then when n equals 6, we have f of 6 plus 2 times f of 6 equals 3 times 6 plus 5. And that means because f of 6 is 1, so 2 times f of 6, or 2 times f of 1. 2 times f of 1 over here equals 3 times 6, 18, plus 5, 23, minus 1, 22. Now, from this, we know that f of 1 equals 11. But this is absurd because we've already found that f of 1 is 6, or I should say we've assumed that f of 1 is 6. So there's a clear contradiction. And we can stop looking at this case. Next, we can take a look what happens when n equals 4. When f of 1 equals 4, then 2 times f of 1 equals 8 minus 4, and that's 4. So f of 4 equals 2. Now putting into the given equation, when n equals 4, f of 4 plus 2 times f of 4 is 3 times 4 plus 5, so it's 17. Then 2 plus 2 times f of 2 equals 17. But we notice that the left side is actually even because it's 2 plus 2 times some integer. So it must be even number while the right hand side is odd. Or we can just solve for f of 2 and we have 15 over 2. But that's not possible because f is supposed to send to a positive integer to another positive integer. But now we have 15 over 2, which is not a positive integer. So again, a contradiction. Now from this we know that we only have one more case to go, and that's f of 1 equals 2. And we can use the same trick, which is that then 2 plus 2 times f of 1 equals 8. And so f of 2 equals 3. Now from this, we can put n equals 2 into the given equation. F of 2 plus 2 times f of 2 equals 3 times 2 plus 5, and that's 11. So 3 plus 2 times f of 3 equals 11, and we have f of 3 equals 4. So now we have 3 values obtained, and still no contradiction at this point. When we put 1, we get 2. When we put 2, we get 3. When we put 3, we get 4. So, and you might want f of n equals n plus 1 to be a valid solution. Now let's see. In fact, I can do this. I can do a claim. For all positive integers n, f of n equals n plus 1. And to prove this claim, we can perform induction on n. From the results above, we know that the statement is true when n equals 1, 2, and 3. To proceed, we can assume that the statement is true when n equals k, which means f of k equals k plus 1. Then when n equals k plus 1, the goal is to prove that f of k plus 1 equals k plus 2. I'm going to put n equals k in the given equation. And I will have f of k plus 2 times f of k equals 3k plus 5. Then by our assumption, f of k is k plus 1, so k plus 1 plus 2 times f of k plus 1 equals 3k plus 5. And by solving, we can see that f of k plus 1 is equal to k plus 2. And so therefore, done by induction. Now from this, we know that since f of 1 equals 2 is the only valid solution for f of 1, and by proceeding, we know that we can only get f of n equals n plus 1 for all positive integers n. That means this is the only solution. And in fact, during the induction, we've actually already checked that is a valid solution. And if you really want to do that formally again, you can see that n plus f of n plus 2 times f of n is just n plus 1 plus 2 times n plus 1 plus 1. And simplifying, you will have 3n plus 5. So this is the final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.